And I'm going to introduce the first speaker of this session. It's Claudio Jecker. He's a long-time OpenBSD developer working on BGPD, OSPFD, OSPF6D, and the MPLS framework in OpenBSD. And he's currently working full-time on OpenBGPD, which is the subject of his talk today. So could you please join me in welcoming Claudio to the stage? Thank you. Oh, I've made a complete... Let's start that again. This is what happens when you don't have coffee. I'm so sorry. Okay. Let's see my notes. There we go. Welcome to the second session of today's technical meeting. How is everyone doing? Some deja vu here. The first speaker of this session is indeed Flemming Heino. Flemming has been working as an IP network designer since the beginning of the commercial internet. He's worked at BT Labs, Level 3 and Packet Exchange, and on a range of projects, including the design of BT's initial business and retail internet offerings, the design of Level 3's initial European IP backbone, and the launch of one of the world's first long-distance multilateral peering services. He is now a senior network architect at LINX, and Flemming will talk about deploying a disaggregated network model at LINX. So please join me in welcoming Flemming to the stage. Thank you very much.
Hello, so welcome. So I'm presenting today about the pretty major project we did at LINX. For those who are not familiar, LINX is the main internet exchange in London, but like AM6 and D6, we also have quite a bit of coverage outside of the UK. So a bit of a background about the project that we did and why we did it. Similar that NetNod has a number of exchanges in a number of different locations, we not only have exchanges across the UK, but even within London, we actually run 2 independent exchanges. Historical reasons, but we still have both. LON2 is a slightly larger, running VPLS and traditional routing equipment. LON2, which is the one this project was related to, at the start of the project was still running traditional Ethernet switching, ring protection, not quite spanning tree, but that generation of technology. We've been trying to move to something like VPLS, but we hadn't been successful. Come 2015, and the economics of 100 gig suddenly kicked in, and we saw a huge increase in orders, and we could draw the new line and realize that sooner or later, we're going to have to change the network. So we knew that LON2, which was reaching the end of its life, something was needed. We're going to outgrow the existing chassis. We'd also need a fair bit of investment on the core. And we wanted to make sure that we didn't just crash into that, but take an early view. We took the opportunity to look and start thinking strategically. So not just solving the same problem, but bigger, but saying, could we do something different? We looked at both ends of the spectrum, traditional vendors, so the kind of the Cisco's, Junipers, Nokia's, I think it was already Nokia in those days, or going in at totally the other end, what was described earlier as the hipster end, which is the white box open networking. And we didn't so much compare vendors, but so what could we do with those strategies? And then for each of the strategies, we compared what was the best vendor for them. The key bit when looking for the strategy was that there wasn't, other than from the traditional router vendor, any solution that would work perfectly out of the box. We have a few requirements that if we take something that based on the 2005-2006 market, really was destined more for the data center market. There wasn't any layer 2 solution that met all our requirements. So we had to work with whichever vendor we picked to incorporate them. And the other bit is, and I think that'll be a thread of this presentation, similar to NetNod being a foundation and not being a pure commercial organization, LINX is a mutual. We're owned by our members. It wasn't just looking at what was the best financially, but it was also what best met the needs of our members. We went in, we talked to all of our members across Europe. We also went to North America, to NANOG, to actually talk to our members and found what strategy, what approach would work better. Now, I said earlier that Internet Exchange parties are different, and I'm going to explain some of the requirements that we had to incorporate beyond just building a stable, reliable, I'm not going to use rock solid as that's trademarked, but equivalent network. So first thing, we have partner ports. So those of you who are familiar with NetNog Reach, we call it connections, same concept. It allows third-party companies to provide connectivity to our exchanges remotely. So if they're more than just a cross-connect range, it's quite an effective way to connect to them. But that technically is a total flip, because now the member is a VLAN. So all the max security features, everything that needs to be done on the port is now on a VLAN. We need to put various quality of service. The allowable broadcasts, unknown and multicast, now moves on to the LAN. And all other member features, instead of being a port, is now on a VLAN. And the thing that really does the head-in of a layer 2 vendor is all those VLANs then get plugged into the same layer 2 broadcast domain. So router, it's fine, it's a subunit, a port unit, a sub-interface, whatever your vendor calls it. That's straightforward. But saying, well, actually, VLAN 100, we want it to map to VLAN 52, 17, and 312 on that port. Their software is not designed for that. The other big thing that we have as an Internet Exchange is max security. If you haven't been in the Internet Exchange business, you probably haven't earlier found a data center trying to find a cross-connect, and deciding the correct way to do that is to put a loop back towards the exchange. Luckily, we worked with our vendors quite a while back to actually put max security. So when that happened, the port basically says, nope, that's not right. But again, new vendors hadn't got implemented those features. The other big thing, in particular using Broadcom, Mac learning is not always a good thing. There's a quirk with the implementation of the ASIC. The learning bit of their fixed pipeline is before the Mac ACL. So they'll learn, they'll consume forwarding power doing the learning, and then they'll drop the frame anyway. And if you have a loop back, that'll basically has a reasonable chance of grinding the whole switch to a halt. The other thing, because we're more of a service provider, we can't design and aggregate and do best practice on our layer 2 domain. We can't have the high-speed servers in their layer 2 reachability, the slow speeds in their reachability. A 1 gig member wants to talk to a 100 gig or n times 100 gig member, so they have to be on the same layer 2 domain. Totally not best practice. It does mean that the flooding that can occur because of a small amount of unknown or multicast traffic on a 100 gig port does really horrible things to someone that only has 1 gig. 200 meg is negligible if you have 2 times 100 gig. If you have a 1 gig port, that's 20% of your service and realistically 30% of your usable bandwidth. And the last big challenge, and that was one on instrumentation, that if you're running a data center and you have some unexpected traffic, you talk to your server guy and say, what on earth are you sending me? It's across a demarcation. We don't have that same visibility. They might be working in different time zones. Usually we talk to their routing team, which is once removed. They might be a transit provider, so it might be 3 or 4 step removed. So if there is some unexpected traffic, we really need to have the instrumentation to find out what it is. And that is, in particular for introducing a new technology, we need that from the start. That is the worst feature you can ever do as a post-launch wish list. So going on to the project, how we started, kind of a bit of a spoiler. We did decide to go for the open networking solution. Part of it is having two networks. We were in a position of taking a risk. We could have gone for a more traditional vendor, and we definitely were talking to Arista. But part of the message we got is that actually if we help the service provider market forwards by actually help creating a market, that would be quite appreciated. So we took a slightly higher risk approach. As the first people with the new vendor, a lot more interaction, a lot more effort. If you remember from Baffin Bay saying there's a lot of time developing, part of the idea is we would do that so that other people can then make use of our development and our features moving forward. So we're in the community-based approach. So the first bit we did, we found a hardware partner. That was EdgeCore Networks, very, very established hardware manufacturer and designer. Good chances a lot of you have actually deployed their equipment. It might just have someone else's badges on it. Most of the major vendors have used their manufacturer and design services. We went with them. Their recommended NOS wasn't the best. Let's be polite and call it at best fragile. I'm not going to name names. I know that company has improved since, but we just saw that the way they were implementing the exchange features and also the approach of that company at that time basically meant, no, we're not going to proceed with them. We called off the POC early. We're about to fly back. Flights weren't available the very next day, so during the one day, instead of just doing tourism in Taiwan, which would have been very tempting, we actually sat down and did a lessons learned. Why did this project fail? And they actually wrote down what we really wanted, probably what we should have done before flying out to Taiwan in the first place. But at least we got the requirements. And they introduced us to IPN Fusion. For those of you who are familiar with Zebra or even Quagga, which is based on it, they're the original developers of Zebra. They became specialist stack vendors. A lot of equipment actually run their bits of their stack within it, either continue manage or just sold as a stack that then the other vendor developed. So maybe less, though, considering one of their major customers was based in this city, maybe more of you have probably used their software. So we worked with EdgeCore to build an initial demo, not quite a POC, but we still tested the solution. The other thing is we didn't know IPN Fusion directly, so we did go through, talk to quite a few people who had worked with them, not in the NOS, not in the white box space, but we started talking to them and actually got references as far as what they're good at, what they're weak at, and their software quality and their QA quality. And the conclusion we got at that point is that because of their ambition and the ambition that EdgeCore had, is that if anyone was going to achieve this within the market and get put in the focus required, it was them. So we kind of went where we want to do this, and if we're going to succeed, these are the right partners. So we went in, agreed a target solution. We really want to jump forwards in technology. We didn't just want to do VPLS or a layer 2 switch. We wanted to also not just have a hardware leap forward, but a technology leap forwards. For those of you who are less familiar with EVPN, it's really taking the concepts of IP routing and applying it properly to layer 2 forwarding. So no looking and snooping and saying, well, if it's come from P number 23, then the return path comes back from P number 23. Much simpler. P number 23, if it learns a MAC address, puts it in a BGP NLRI, sends it to all other Ps, and the other Ps then know about it. Unidirectional paths, all those forwarding and data plane learning bugs, they're all gone. So it's much it's a new technology, but it's using really established concept. And the beauty with it is the same way as if you don't have a default route, if you have a packet destined to an IP address that's not in your routing table, you drop it because you know that no router in your network knows about it, or if there is one, you've done it as a policy. The same way, if a MAC address is not known, you now can drop it. So all of that, well, we'll give them that much unknown flooding just in case. That's out of the window. You can really turn the screw on reduction of the background traffic because you can take the approach. Now, if it's not known at that switch, no other switch knows about it. And also it opens multi-homing as a future enhancement. Question occasionally got asked is why did you not go for the kind of the central controller SDN based approach? Not too much there, but basically we started as a networking company. We were building a software team, but they were working a lot on automation, particularly automation of our LON2 network. Having them all of a sudden build or maintain a really reliable mission-critical controller would have been a step too far. We wanted to work with IDNA and mature our software team instead of telling them, oh, by the way, in 1 year's time, you're going to be doing the mission-critical function for our key business. So that was really our decision and selection phase. As you can see live, it's quite a gap. It was, being absolutely honest, it's larger than we thought. Luckily, because we consulted with our membership, we had the support for that process, but we definitely did have a number of surprises on that process. The first big one we had was MPLS labels. Associated with the chip we picked, we could have picked a different one halfway through, but they had different limitations in any case. But one key limitation you have is the number of labels you can either add to the stack and remove to the stack, and in particular, remove to the stack. So the ESI label, which is required for MPLS load sharing, that's 2 labels. So if you can only pop 3 labels at a time, 2 of them on ESI is gone. Sorry, not ESI, entropy labels. The ESI label, which is a EVPN feature to allow multi-homing, which was our ambition, that again is 1 extra label that really didn't fit. We did have a solution and a prototype that worked, but if you read the RFC and you read the implementation, you'd notice they didn't work. And bottom line, if we did that, we would probably not manage to interop with anyone else's EVPN implementation. So it would have solved multi-homing, but the whole point of having standard-based multi-homing is somewhat defeated if you do it in a proprietary manner. The other thing that was quite a concern from Broadcom is they really, when they were designing, were thinking of VPLS. And VPLS, because it needs to learn, every single remote PE has its unique label, whereas one of the simplifications you have with the VPN is the label it purely designates the egress PE. So you don't have multiple bidirectional tunnels. You actually have a merge label for all remote PEs. So that was something they just hadn't tested, and they said if you do go down that path, here's a whole list of extra tests that needs to be done. And the last thing that really came in is that every LSP consumes, if you set up an LSP in a P router, an LSR, that actually takes an entry in the interface table. And when you build your core, and remembering you can't use multi-homing, so you have to do multiple parallel paths for hashing. And on a full mesh, it's n squared. We kind of counted how many edge routers we'd had, until all of a sudden the core routers were just going to run out of interface tables. And because of the economics of silicon and memory, it didn't look that whenever the chip density was going to double, the interface table was going to double. The indication we're getting from Broadcom was actually, no, that's more or less going to stay constant. So it wasn't the case that we could buy twice as big a router and the problem would go away. We'd actually buy twice as big a router and still be able to use the same number of ports. The one important bit, this is not a go at Broadcom. They were hugely supported across the whole process. They were giving us quite a few feedbacks and suggestions. It wasn't a, don't go there, this is scary. It's, well, no, let's solve this. And they created this market. So just want to make sure that I don't it was decisions they made for a very good reason, that we were trying to use the equipment for something else, and we found limitations associated with it. So a much better solution for our need was VXLAN. It's another overlay network. Even though we'd spent a while working on MPLS, IP and Fusion were already working on VXLAN transport for other customers, but without the exchange features. But those modules were relatively easy to carry across. The EVPN work, that was all reusable. So no ESI labels, always a nice bonus. The UDP source port instead of entropy label, so a lot of the extra information that needs to come in was coming in. So yes, we could work with that. Not first choice, new technology for our team, but the two big concerns we had is A, the real information, the tunnel statistics we could get for the traffic engineering and forecasting. Analysis was it was good enough. Convergence, because you don't have quite the same fast reroute. It's not as good, but we expected it to be good enough. We'll get back. Well, actually, next slide is actually on that. So on the convergence, kind of the big, what we thought was going to be the big compromise is for LON2, we have a target of, for most failures, converging sub 50 milliseconds. That's the target fast reroute time. That's what most application developers are told. Well, your network will have up to 50 millisecond blips. So if the application is designed around that, they shouldn't notice events. For VXLAN, in particular IP fabric, the topology is key. And that because you both have to recompute the forwarding path and get your actual fib correct, but then you have to push it down to the ASIC, and it does actually take a non-negligible amount of time, and actually the reprogramming of the ASIC often was faster than recomputing on the control plane. And the worst case that we found is if the reroute occurs on the first hop of the network. So when it flips from next hop A to next hop B. So there's just all that VXLAN state where you actually are reprogramming the tunnel. There's also forwarding on the tunnel that needs to be reprogrammed. We saw 300 to 600 milliseconds. If the reroute is not at the first hop, it's 150 to 300. Not quite the 50, but still closer to it. And to explain the reconvergence, this would be if it was an example at the first cut, at the first hop. So if you have a fiber going east, a fiber going west, and switches handing them, if you have the fiber cut, the reroute occurs on the ingress. You can see, that's a button. You can see that's where the reroute occurs, and that means VXLAN tunnel changes, lots of programming, slow update. If, on the other hand, you put a spine, so really go for the textbook leaf and spine cloth fabric, if you have a fiber cut, it's now the spine switches that do the reroute. The next hop for the tunnel is unchanged. At worst, you have the loss of a spine switch, but even in that case, this is now ECMP. This is not actually a reroute. This is going from two paths that are already programmed and say, well, remove one. That's much, much faster. That is in the 50 to 100 millisecond. And if it's an ECMP reroute, it is about 50 milliseconds. And if it's individual parallel links, those are well below 50 milliseconds, actually usually sub 10 millisecond. Other side effect on convergence we have is there's a hold time at repair. There's a small hit if it's not in a load sharing configuration, but it's still sub 50 milliseconds. And we added a few things so that if there was churn or flapping interfaces, it would kind of go and kind of take it down, call the engineering department. We won't look at that link until the engineering department have given us the all clear in software, but essentially that logic. And the key bit, it was much better than the previous LON2 convergence times. Not quite as good as our LON1s, which are based on very expensive silicon, but much faster. So brief summary of the solution. So first thing, we went for leaf and spine architecture. As I indicated, one of the big things we had as a shock is we needed to upgrade the router. Whereas here, the approach we had was we essentially scaling up, not. So we actually, you can add more components instead of upgrading the whole router. So the whole approach the industry has learned from the hyperscale data centers is you can scale horizontally instead of making each of your components bigger. And that means it's easier to grow the network faster, also because it's much more simple building blocks, you can have a lot more spare. The other thing that we said, not only do we have EVPN and we gave the advantage it has for flooding, but even if you use the same mechanism to propagate IP, you get proxy ARP coming in as the propagation of IP addresses. And that means that not only do all the Ps know about all the MAC addresses, but they also know about the IP ARP resolution. So when an ARP comes in, instead of it being flooded to every other PE, every other C, every other member of the exchange, the ingress PE just says, okay, that's the answer, and no one gets disturbed. The last feature that we had is MAC hold down, and that's something we'd done as far as analysis and we'd seen on the old behavior, which is that if a port goes down, because the FDB entry is pointing to interface number 23, interface number 23 will just remove the entry in the forwarding table. All the other routers will take a while to find out about it, but they're the ones that actually rate limit the ingress table, the unknown traffic. So up until the networks converge, actually all the traffic destined to that port gets flooded to all the other ports on that switch up until the whole network has reconverged. It was really bad in the VPLS days because that was actually a MAC age out, and on the layer 2, again, it was a MAC age out. At least it's somewhat faster with the VPN because it's a BGP push. So you're talking about 4 or 5 seconds as opposed to 2-3 minutes. But the mechanism we did instead is we had a floating default route. So if a port goes down, we actually replace the route to the interface with a temporary route to dev null, which drops that traffic up until BGP converges. And it means that actually there is no local flooding. So that is a before, as we're doing migration, and there was one 1 gig probe that we had left that I grabbed the stats. And you can see if something is averaging 200 megs on a 5-minute average, you know it's instantaneously going to be hitting line rate. So that port, okay, it was a performance monitoring port, and we migrated it last, not first. But you can see that performance monitoring probe really had a hard time with it. I couldn't actually get a good graph post. It's just a flat line. So as a recap, and I'm going to finish on this because I'm a little behind on time on this one. What we did deliver through this network was a solution that not only was innovative and that allowed the marketplace hopefully to take advantage of our leads and our benefits on getting the stability right, but also being a mutual organization, something of benefit for all our members. So the small members, their big issue was flooding, and that was addressed by the technologies we came in. Our larger members, their biggest issue is every so time they would order 2 times 100 gig without telling us, and they want it in 3 weeks' time. Actually being able to scale the network fast is of significant benefit for them. And as much as we're mutual, we still do have the real world significantly lower cost. So I'll finish at this point. And do I have time for questions, or?
For one very quick question, if anyone has a question, just raise your hand. No? Okay, well then please join me in thanking Flemming for a very nice presentation. Thank you.